Tonight, we're going to explore the Andromeda Galaxy. It's out there right now, visible tonight. If your sky is dark enough and you know where to look, a faint, pale smudge hovering just to the northeast of a familiar pattern of stars, quiet and almost invisible, easy to pass over, easy to lose. Most people who see it think it might be a cloud, or a smear on the lens, or just a slightly brighter patch of the Milky Way that their eyes can't quite resolve. Something to glance past on the way to something more obvious. Here is what it actually is. That pale smudge contains 1 trillion stars. Its full width, if you could see all of it, spans 6 times the diameter of the full moon across the sky. The light entering your eye right now left that galaxy 2.537 million years ago, before our species existed, before the first stone tools, before anything alive on this planet had learned to look at the night sky and wonder about it. And that smudge, that small, easily overlooked thumbprint of light, is not staying where it is. Andromeda is not drifting peacefully in some far corner of the cosmos. It is not receding from us the way almost everything else in the universe is. It is approaching, right now, at roughly 250,000 miles per hour. It has been closing the distance between itself and the Milky Way for longer than the Earth has been a solid world. And what that approach eventually means for our galaxy, for every star in the sky above you, for the future of everything in our corner of the universe, is one of the most profound stories in all of astronomy. And by the end of tonight, you're going to understand exactly why. If this kind of exploration is what you come here for, a like or subscribe keeps slow orbits going and helps others find their way here. Now, let's begin. Let's start with something that almost never gets stated directly. Most people have never seen another galaxy. They've seen photographs of galaxies, the sweeping, color-enhanced spirals in Hubble images, the vast whirlpool structures in astronomy textbooks, the glowing disks posted on museum and planetarium walls. They understand, in an abstract way, that the universe contains hundreds of billions of galaxies, but they haven't stood in a dark field and looked up and seen one with their own eyes, except that many of them have. They just didn't know it. Under reasonably dark skies, away from city lights, on a clear autumn night in the northern hemisphere, the Andromeda Galaxy is visible to the naked eye, not as a spiral, not as a disk of stars, but as a faint, elongated smudge of light, easily missed, easily confused with something else, but undeniably there when you know where to look. Finding it takes only a few minutes once you know the route. You begin with the Great Square of Pegasus, 4 moderately bright stars arranged in a roughly square pattern that dominates the autumn sky in the northern hemisphere. These are not the 4 brightest stars you'll see, but they're distinctive in their arrangement, an empty box of sky in an otherwise busy region. From the northeastern corner of that square, a chain of stars extends upward and to the left, marking the constellation Andromeda itself. The second star in that chain is Merak, an orange-red giant, distinctly warmer in color than the white and blue-white stars around it, so it stands out. From Merak, you move upward through two fainter stars, one called Mu Andromedae, one called Nu Andromedae, and then shift slightly to the right. That's where you're looking. And then you see it, under genuinely dark skies, the kind where you can see the full arc of the Milky Way, where the zodiacal light is faintly visible, where your eyes need 15 minutes to fully dark adapt before you can trust what you're seeing. Andromeda appears as a soft, oval glow, a little brighter at the center and fading smoothly toward the edges. It doesn't sparkle the way stars do. It doesn't have a sharp point. It has the quality of something illuminated from within rather than shining as a point source. Experienced observers describe it as something between a cloud and a breath on glass, present, real, and yet somehow uncertain, as if it might disappear if you look directly at it. Many people who see it for the first time mistake it for a patch of the Milky Way. When you shift your gaze slightly off to the side and use peripheral vision, which is more sensitive to faint, diffuse light, it becomes more distinct. It doesn't respond the way stars respond. It doesn't disappear when you use averted vision. It brightens. It's too big, too evenly lit, too smooth to be a star. Binoculars change the experience dramatically, with even a modest pair, 7x or 10x magnification. The galaxy reveals itself as an elongated oval with a brighter core and gradually fading edges, clearly not a star, clearly structured, clearly enormous compared to the stars surrounding it. You can see that it has extent in 2 dimensions. It fills the field of view of small binoculars entirely. You begin to sense the scale of it. A small telescope at low magnification shows something more. Dust lanes begin to appear, dark bands of interstellar material threading through the disk, interrupting the smoothness of the light. These are not optical imperfections, they are physical structures inside the galaxy, clouds of gas and dust so dense they absorb the light behind them, creating dark channels visible from 2.537 million light-years away. You are looking at the actual structure of another galaxy. A larger telescope at low power reveals the outer disk spiraling outward from the core and resolves the 2 satellite galaxies M32 and NGC 205 as distinct companion objects nearby. M32 appears as a small, compact, nearly circular glow southeast of the main disk. NGC 205 appears as a larger, more diffuse, elongated patch to the northwest. Each step up in aperture reveals more. But what the naked eye sees is already profound if you let it be. Now think about what you're actually looking at. If you hold your arms straight out and make a fist, the width of your knuckles covers roughly 10 degrees of sky. The moon covers about half a degree, a small coin held at arm's length. Andromeda if you could see its full extent, spans approximately 6 degrees from end to end, more than 3 fists wide, more than 6 moons laid side by side across the sky. But what the naked eye sees is only the central region, the compressed brightness of the core, because the outer reaches of the galaxy are too faint, too diffuse, too spread across the sky for eyes calibrated to brighter objects. What we see represents perhaps a tenth of the galaxy's actual angular extent. A telescope at low power shows more of it. Long exposure photographs show all of it. An enormous structure that dwarfs anything the eye can register from the ground. And the reason it appears so small is the same reason it appears so faint. It is incredibly far away. What you're seeing in that pale smudge is the collective light of approximately 1 trillion stars. 1 trillion. It's worth letting that number arrive rather than rushing past it. If you tried to count to 1 trillion at one number per second without sleeping, without stopping, without slowing down, it would take you roughly 31,688 years, not 31,688 seconds, years. The entire span of recorded human civilization, from the earliest known writing systems of ancient Sumer to this moment, spans approximately 5,000 years. Counting to 1 trillion would outlast that entire record 6 times over, and then continue for more than 21,000 additional years after the end of everything human beings have ever documented. And that count would represent one data point about what that faint smudge contains. The Milky Way itself holds somewhere between 200 and 400 billion stars. Our uncertainty in that number reflects the genuine difficulty of counting objects distributed through a 3-dimensional disk, 100,000 light-years across when you're standing inside it, and can only work with the light that has had time to reach you. But even at the high end of our estimates, the Milky Way has fewer stars than Andromeda. Andromeda is a slightly more massive galaxy than our own. It contains roughly 1.5 trillion solar masses of material compared to the Milky Way's estimated 1 trillion solar masses, which means that in the eventual gravitational relationship between these two systems, Andromeda is, very slightly, the dominant partner. And yet, it appears smaller than your thumbnail. This tension, 1 trillion stars, smaller than a thumbnail, is a calibration. It tells you something precise about distance, about what distance actually means at astronomical scales, because the light that makes up that pale smudge in your sky has been traveling for 2.537 million years. 2.5 million years of crossing intergalactic space through the thinnest possible haze of gas and the occasional rogue star ejected from its home system, traveling at 186,000 miles per second, the constant speed of light, the same for every photon from every source in the universe, until it arrived at Earth and entered your eye. That light left Andromeda at a moment in Earth's history that is worth describing carefully. 2.5 million years ago, The Pleistocene epoch was just beginning. The global climate was shifting into the first of a long series of glacial cycles. Ice sheets were advancing across the northern continents, reshaping coastlines and river systems and the ranges of animal species. In Africa, in the great grasslands and woodlands of the East, a new genus of primate was appearing in the fossil record. Early members of the genus Homo, the genus that would, after another 2 million years of evolution, produce our own species, were leaving their traces in stone. Simple tools, flakes chipped from rock, used to cut meat or break open bone for marrow. The brains behind those hands had crossed some threshold of capability without yet producing language, without fire, without any of the things that would eventually create civilization. Mastodons were alive. Cave bears were alive. The northern continents were being slowly overrun by ice. Every major river system on Earth was running along a slightly different course than it runs today. The distribution of coastlines, where the land ended and the ocean began, was measurably different because so much water was locked up in ice. The world was recognizable, but not identical. The light you see in Andromeda tonight crossed all of that time. The night sky above those early humans contained Andromeda, the same pale smudge you might see tonight, perhaps slightly brighter from a darker world before human fire spread across the landscape, but the same object, the same light more or less, because 2.537 million years is not a long time for a galaxy. Andromeda was not meaningfully different then from what it is now. This means that Andromeda has been visible to naked eye observers for the entire duration of our genus. For every human being who has ever lived, on every clear autumn night in the northern hemisphere, Andromeda has been there, that faint oval in the sky, overlooked by almost everyone, identified by none for most of our history. Every Egyptian astronomer who mapped the sky, every Babylonian scribe who recorded planetary positions, every Greek philosopher who argued about the structure of the cosmos, every medieval scholar who measured stellar positions with brass instruments. They all lived under a sky that contained Andromeda. Every generation of humanity has had access to it. Almost none knew what it was. The most distant thing the unaided human eye can reach. 2.5 million years of history overhead, present on every clear autumn night, unknown in its true nature until 1924. Think about what that means for the history of astronomy. For centuries, astronomers catalogued objects in the sky with extraordinary precision. They measured the positions of stars to fractions of an arc-second. They tracked the orbital motions of planets to accuracies good enough to navigate by. They built instruments of increasing sophistication, developed mathematical frameworks of increasing power, and brought to the sky a rigor and patience that produced one of the great intellectual traditions in human history. And the whole time Andromeda was there, recorded by Al-Sufi, catalogued by Messier, discussed by every major astronomer of the Enlightenment, visible on every clear autumn night from every observatory in the northern hemisphere, a fuzzy oval in the catalogue, a cloud among the clouds. The universe hid its true scale in plain sight for most of our history, not because we lacked the observations, we had them, but because we lacked the tools to interpret them correctly. A measurement that could determine the distance to a variable star in another galaxy required technology that took a specific sequence of scientific developments over more than a century to produce. The photographic plate, the large reflecting telescope, the period luminosity relation, all of it had to be assembled before the question could even be asked in a form that admitted an answer. The question was always there. The galaxy was always there. The universe was always as large as it is. We just hadn't yet built the tools to know it. There is something quiet about that fact, something that rewards sitting with it rather than moving on quickly. Let's spend some time on the structure of Andromeda itself. Not just the numbers, though the numbers are important. The physical architecture, what it looks like, how it holds together, what its interior is made of. Andromeda is a spiral galaxy. In the standard classification systems used by astronomers, it is grouped as an SASB type, a spiral galaxy with a moderately wound set of spiral arms, without a strongly pronounced bar through the center. Though recent analyses using infrared imaging have found evidence of a mild bar structure that was difficult to see in optical wavelengths through the galaxy's own dust. It is broadly similar to the Milky Way in type and structure, which is why the two are often called twin galaxies, though they are not identical, and the similarities are not perfect. Like the Milky Way, Andromeda has several distinct structural components. At the center is the bulge, a dense, roughly spherical region of older stars, predominantly yellow and orange and red. These are ancient stars, many of them more than 10 billion years old, formed in the first few billion years of the galaxy's existence. They burn slowly, consuming their nuclear fuel at a pace measured in billions of years, and their combined light gives the central region of Andromeda its characteristic warm glow visible in photographs. Stars in the bulge do not orbit the center in the organized coplanar paths that stars in the disk follow. They orbit in complex, overlapping three-dimensional paths, contributing to the smooth, non-turbulent appearance of the central region. The bulge is quiet, old. Most of the dramatic activity in Andromeda happens farther out. Extending outward from the bulge is the disk, a flattened structure of younger stars, gas and dust, organized into spiral arms. The spiral arms of Andromeda are prominent in ultraviolet and blue light, which picks out the hot young stars that form preferentially in the denser regions of the arms. These are the blue-white stars, massive, luminous, burning through their hydrogen at prodigious rates, that trace the locations of active star formation. They live only a few million years, dying in supernova explosions before they can drift far from their birthplaces, so their positions mark the regions where gas is currently dense enough to collapse. In visible light, and especially in infrared, the spiral arms are traced by dust lanes, dark bands of interstellar material that cross the galaxy's face in photographs, curving dark lines interrupting the smooth oval of the disk. These dust lanes are not obstructions in any simple sense. They are regions where interstellar material has accumulated into dense clouds, and where that material will eventually collapse under gravity to form new generations of stars. They are the factories. The raw material for the galaxy's future is sitting in those dust lanes right now. Andromeda's star formation rate is currently estimated at roughly 1 to 2 solar masses per year, meaning that each year the equivalent of 1 to 2 times the Sun's mass in new stars is formed somewhere in the galaxy. This is somewhat lower than the Milky Way's estimated rate of a few solar masses per year, and much lower than the intense starburst rates seen in actively colliding galaxies. Andromeda, like the Milky Way, is in a relatively quiet period of its life, a middle-aged spiral that formed most of its stars billions of years ago and is now producing new ones at a modest, sustainable rate. Both galaxies have already consumed a large fraction of the interstellar gas available for star formation in their early years. The raw material for future stars, the gas and dust that makes up the interstellar medium, is still present in Andromeda's disk, but it is distributed differently than it was in the galaxy's youth. In the early universe, galaxies were gas-rich systems, with large fractions of their mass in diffuse gas clouds that rapidly collapsed into stars. Over billions of years, successive generations of stars have processed that gas, converting it from hydrogen and helium into heavier elements inside stellar interiors, then returning those elements to the interstellar medium through stellar winds and supernova explosions. The gas we see in Andromeda's disk today is richer in heavy elements than the gas that formed the galaxy's oldest stars, because it has been through multiple cycles of stellar processing. In radio wavelengths, particularly the 21 centimeter emission line produced by neutral hydrogen, Andromeda is a dramatically different object than it appears in visible light. Radio telescopes reveal the full extent of the neutral hydrogen disk, which extends far beyond the optical disk visible in photographs. The neutral hydrogen traces the spiral structure but also shows subtle warps and asymmetries not obvious in the visible light image, evidence of the galaxy's interactions with its satellites and with the general gravitational environment of the local group. The outer hydrogen disk of Andromeda is slightly lopsided, its geometry not perfectly symmetric around the galactic center, a signature of the galaxy's history that persists in the gas long after the triggering interaction has receded. Andromeda also emits X-rays. The X-ray emission comes from multiple sources: a general diffuse glow from hot gas in the halo, heated to millions of degrees by supernova shockwaves and by the injection of energy from stellar winds, and hundreds of point sources distributed across the disk and bulge. These point sources are mostly X-ray binary systems, pairs of stars in which one member is a neutron star or black hole actively accreting material from its companion. Each one represents a stellar remnant from a long-dead, massive star, still dynamically active, still processing the material around it through gravity and radiation. The inventory of X-ray sources in Andromeda gives astronomers a census of compact objects, neutron stars, black holes, distributed through the galaxy. The Milky Way has a comparable inventory, though we see our own galaxy through the dust of the disk, which makes the census there much harder to complete. Surrounding the disk and bulge is the halo, a diffuse, roughly spherical region extending far beyond the visible disk. The halo contains the oldest stars in the galaxy, arranged in loose associations and in spherical clusters called globular clusters. The Milky Way has approximately 150 to 200 known globular clusters. Andromeda has more than 450 confirmed, with additional candidates being identified as imaging surveys improve. These globular clusters are ancient things, dense spheres of hundreds of thousands to millions of stars formed in the earliest 1 billion or 2 years of the galaxy's life. They are time capsules preserving chemical information about the conditions that existed when the universe was young. The stars in the oldest globular clusters contain almost no elements heavier than hydrogen and helium, carbon, oxygen, iron, silicon. The heavier elements that make up planets and living things had not yet been forged in sufficient quantities in stellar interiors and returned to the interstellar medium when these clusters formed. The absence of those elements in the oldest stars is a record of the universe's own chemistry before most of its history had happened. There is something visible around Andromeda that becomes apparent in very deep, long-exposure photographs. A vast system of stellar streams, ribbons of stars wrapping around the galaxy's outer regions, some extending tens of thousands of light years. The largest of these is sometimes called the Giant Southern Stream or the Great Stellar Stream, visible as a curved arc of stars sweeping south of Andromeda's main disk. This stream is the debris of a galaxy that Andromeda has already consumed. A smaller system, perhaps once a satellite galaxy, perhaps a dwarf galaxy that wandered too close over billions of years, was torn apart by Andromeda's tidal gravity. Its stars were pulled into long ribbons, gradually dispersed around the larger galaxy, now marking where that smaller system used to be. Andromeda is not currently in an isolated state. It has a history of consumption, a history of absorbing smaller galaxies into its bulk over cosmic time. The Milky Way has its own version of this. The Sagittarius dwarf galaxy, discovered in 1994, is currently being absorbed by the Milky Way, its stars drawn out into a vast loop wrapping around our galaxy's outer regions. Both galaxies have eaten before. What surrounds them in the outer halo is partly the remains of smaller objects they have absorbed over their lifetimes. Andromeda's halo is remarkably large. Measurements using the light of individual halo stars and of background quasars have established that Andromeda's stellar halo, the region containing stars clearly associated with the galaxy but far beyond its visible disk, extends to at least 2 million light-years from its center. At that scale, the outermost reaches of Andromeda's halo already overlap spatially with the outermost reaches of the Milky Way's own halo. The two galaxies are, in the loosest sense, already touching, their tenuous outer envelopes already interpenetrating, even though the visible disks, the bright spirals we identify as the galaxies themselves, remain 2.537 million light-years apart. Orbiting Andromeda as companions are at least a dozen smaller galaxies. The most prominent are M32, a compact, surprisingly dense, small elliptical galaxy sitting close to Andromeda's disk, and NGC 205, also called M110, a larger and more diffuse dwarf elliptical appearing as a faint, elongated patch south of the main disk. M32 is particularly interesting because it is anomalous. It is far more dense and concentrated than typical dwarf elliptical galaxies of similar luminosity. The current best explanation is that M32 was once a more normal spiral galaxy, possibly comparable to the Triangulum galaxy in size, whose outer disk was stripped away over hundreds of millions of years of close gravitational interaction with Andromeda. What we see now as M32 is the remaining core, the dense central region that was too tightly bound to be pulled away, while the outer disk was tidally disrupted and absorbed into Andromeda's structure. The stripped stars from M32's former disk may be part of the extensive stellar streams that surround Andromeda today. M32 itself has almost no gas, almost no dust, and almost no ongoing star formation. A spent object orbiting the galaxy that consumed everything it once had beyond its innermost regions. Now, let's talk about Andromeda's center. At the heart of most large galaxies sits a supermassive black hole. The Milky Way's central black hole, Sagittarius A star, has a mass of approximately 4 million times that of our Sun. This is toward the lower end of the known range for supermassive black holes in spiral galaxies, and is considered fairly typical for a galaxy of the Milky Way's size. When astronomers first tried to measure the central black hole of Andromeda, they expected something broadly similar. What they found was approximately 35 times more massive. Andromeda's central supermassive black hole has a mass of approximately 140 million solar masses, 140 million times the mass of our Sun, compressed into a region smaller than our solar system. An event horizon, the point of no return, that would extend to roughly 2.5 astronomical units from the center if this black hole occupied our solar system, swallowing Mercury, Venus, Earth, and Mars inside it. And the center of Andromeda is stranger still. When the Hubble Space Telescope examined Andromeda's core in detail in the early 1990s, astronomers expected to see a single bright nucleus. Instead, they found two distinct concentrations of stars in the center of the galaxy, separated by only about 5 light-years, designated P1 and P2. P2 coincides with the position of the supermassive black hole. P1 is offset from the center and is actually the brighter of the two, despite not being where the black hole is. The theoretical model developed by astronomer Scott Tremaine in 1995 explains P1 as a disk of stars in eccentric orbits around the central black hole, a ring of stellar objects whose elliptical paths carry them closest to the black hole at one end and farthest away at the other. Stars in an eccentric orbit spend more time near the far point, a consequence of Kepler's second law. So the region that appears brightest is not the region closest to the black hole. It is the region where the orbiting stars are slow, far away, and spending the most time. P2, where the black hole actually sits, appears dimmer in brightness maps, not because the black hole is less massive there, but because fewer stars linger near the pericenter. The architecture is a gravitational illusion of sorts, surrounding all of this visible structure: the disk, the bulge, the halo, the globular clusters, the stellar streams, is the dark matter halo. Dark matter is the invisible, non-luminous component that provides most of the gravitational mass of any large galaxy. We cannot see it. It emits no light, absorbs no light, and interacts with ordinary matter only through gravity. We infer its presence from the motion of stars and gas, the fact that the outer regions of galaxies rotate faster than the visible mass alone could explain, requiring additional mass distributed in an extended, roughly spherical halo around the disk. Andromeda's dark matter halo extends far beyond the visible disk, potentially to 1 million light-years or more in radius. The total mass of dark matter associated with Andromeda is estimated at several trillion solar masses, far exceeding the mass of the visible stars. The dark matter halos of Andromeda and the Milky Way are already interpenetrating given their extent and their proximity. Gravity from these extended dark halos is part of what is pulling the two galaxies toward each other right now. For more than 900 years of recorded astronomical history, Andromeda was a cloud. The Persian astronomer Abd al-Rahman al-Sufi documented it in 964 AD in his Book of Fixed Stars, one of the great works of medieval science, a systematic catalogue of stellar positions and brightnesses combining Greek astronomical data with new Islamic observations. He described Andromeda as a little cloud, an object that couldn't be resolved into individual stars, that sat in the sky and didn't move with the planets or behave like a comet. He noted it, catalogued it, and moved on. The note persisted. Over the following centuries, every astronomer who systematically catalogued the northern sky encountered it and recorded it similarly. In 1771, Charles Messier compiled the most widely used catalogue of such fuzzy objects, designating them M1, M2, M3, and onward. The Andromeda Galaxy is Messier 31, the 31st entry in a catalogue Messier compiled ironically as a list of things to ignore while searching for comets. These nebulae kept confusing him by looking like comets that never moved. His catalogue was not intended as a catalogue of interesting objects. It was a catalogue of obstacles. Through the 18th and 19th centuries, telescopes improved, and the catalogue of nebulae grew. So did the debate about what they were. Some nebulae, particularly the round, shell-like objects we now call planetary nebulae, were clearly gas, clearly associated with individual dying stars, clearly local. But the spiral nebulae were different. Their structure, visible in long-exposure photographs taken in the late 19th century, had a kind of organized complexity, pinwheel shapes, delicate arms, a central concentration that didn't look like any known gas cloud. To some astronomers, the spiral nebulae looked like they might be made of stars. The dominant view through most of this period held that everything visible in the sky was part of a single, enormous system, the Milky Way. The universe and the Milky Way were effectively the same thing. The spiral nebulae were smaller objects within the Milky Way, perhaps gas clouds collapsing to form new solar systems, perhaps distant glowing regions of ionized gas, but definitely part of our galaxy. The universe was large but bounded. The German philosopher Immanuel Kant had proposed an alternative in 1755 using the term island universes to describe the possibility that the Milky Way was one of many separate stellar systems, and that the spiral nebulae might be others, each one an enormous collection of stars comparable to the entire Milky Way, separated from us by distances beyond anything astronomical measurement had yet achieved. It was an elegant idea, fitting the available observations without contradicting them. But it was an idea without evidence, a philosophical proposal rather than a scientific result. Evidence required a measurement. The measurement required technology that did not yet exist. By 1920, the technology was beginning to exist, and the debate came to a head. The Great Debate was held on the evening of April the 26th, 1920, at the United States National Museum in Washington, D.C. The two astronomers who faced each other that evening were Harlow Shapley and Heber Curtis, and the formal question before them was the scale of the universe and the nature of the spiral nebulae. Shapley, at the time working at Mount Wilson Observatory, had spent years measuring the Milky Way using Cepheid variable stars, a class of pulsating star whose brightness varies in a predictable rhythmic cycle. By measuring the distances to globular clusters scattered around the galaxy, he had established that the Milky Way was much larger than previously estimated, that the Sun was far from its center, and that the entire system spanned roughly 300,000 light years. This was an important and largely correct set of results. From this large Milky Way, Shapley drew an additional conclusion. If the spiral nebulae were at the distances required for them to be comparable in size to the Milky Way, those distances would have to be almost incomprehensibly enormous. It was simpler and seemed more consistent with some available data to conclude that the spiral nebulae were small, local objects within the Milky Way. One piece of problematic data deserves mention. A Dutch astronomer named Adriaan van Maanen had published measurements claiming to detect the rotation of the Andromeda Nebula from photographs taken years apart, a faint but apparently real angular shift of the spiral structure over time. If that rotation were real, the galaxy had to be close. A distant galaxy rotating at that angular rate would require its outer edges to be moving faster than light, which was physically impossible. Shapley took this measurement seriously. It turned out, years later, to be completely wrong, a systematic error in van Maanen's measurement technique, but in 1920 it was a data point in Shapley's favor. Curtis argued the opposite. The spiral nebulae were separate galaxies, island universes, each comparable to the Milky Way. He pointed to the rate of nova explosions observed in the Andromeda Nebula over previous decades. These stellar flares occurred at a rate consistent with a large system containing hundreds of billions of stars, not a small local nebula. He pointed to the fact that spiral nebulae avoided the plane of the Milky Way. An odd distribution if they were objects within our galaxy, but perfectly sensible if our galaxy's own dust-laden disk was blocking our view of more distant objects behind it. Both men presented genuine evidence. Both men were right about some things and wrong about others. Shapley correctly identified the large size of the Milky Way. Curtis correctly identified the spiral nebulae as separate systems. The debate ended without resolution that evening. The question remained genuinely open, honestly contested, with good data on both sides. Resolution arrived not through debate, but through one measurement made in the dark. In October 1923, Edwin Hubble was examining photographic plates taken of the Andromeda Nebula with the 100-inch Hooker telescope at Mount Wilson Observatory, the most powerful telescope in the world at that time. The Hooker telescope's primary mirror was 100 inches across, 8 feet and 4 inches of polished glass, capable of gathering more light in a second than the human eye gathers in an hour of observation. Hubble had been photographing the Andromeda Nebula over a series of nights, looking for novae, ordinary stellar explosions common enough in any large star system to serve as markers. He found what appeared to be 3 of them and marked them on his plates with an N for nova. Then he compared those plates with earlier photographs from the same telescope. One of the objects he had marked was not behaving the way a nova behaves. A nova brightens rapidly over a few days, then fades over weeks. This object was brightening and dimming in a regular repeating cycle, rising to peak brightness, falling back, rising again, with a rhythm that Hubble quickly recognized. He crossed out the N. He wrote VAR on the plate with an exclamation point, an annotation that has become one of the most significant in the history of science. It was a Cepheid variable star. This recognition mattered enormously because of work published 11 years earlier by an astronomer named Henrietta Swan Leavitt, working at the Harvard College Observatory. Leavitt was employed as a human computer, one of a group of women hired to perform the skilled work of measuring and cataloging thousands of stellar images on photographic plates. The work was demanding, repetitive, and low-paid. Women computers at Harvard were paid 25 cents per hour. They were not expected to do original research. They were expected to execute assigned tasks. Leavitt did both. She had been systematically measuring the brightnesses of stars in the small Magellanic Cloud, a companion galaxy to the Milky Way, visible from the southern hemisphere. Over years of painstaking work examining thousands of photographic plates, she catalogued 1,777 variable stars, and she noticed something in the Cepheid variables. Stars with longer periods of variation were consistently, intrinsically brighter. The relationship was smooth, regular, and calibratable. In 1912, she published the full quantitative version of this relationship. Because all the stars in the small Magellanic Cloud were at essentially the same distance from Earth, differences in apparent brightness corresponded directly to differences in intrinsic brightness. Leavitt's period luminosity relationship transformed Cepheid variables into standard candles, objects whose true intrinsic brightness could be calculated from their period of variation alone. Once you know how bright something actually is, comparing that to how bright it appears in the sky gives you the distance directly. The apparent brightness falls off as the square of the distance. The dimmer it appears relative to its known intrinsic brightness, the farther away it must be. Hubble measured the period of his Cepheid in the Andromeda Nebula, 31 days. From the period luminosity relationship, he calculated the star's intrinsic brightness. He compared that to the apparent brightness on his photographic plate. The result? The star was approximately 900,000 light-years away. Shapley's entire Milky Way was 300,000 light-years across. This single variable star, by Hubble's calculation, was 3 times farther away than the most distant edge of the universe Shapley had described. The Andromeda Nebula was not inside the Milky Way. It was far outside it. It was a separate galaxy, a full-scale stellar system containing billions of stars separated from us by almost 1,000,000 light-years. Hubble sent Shapley a letter with his results. Shapley, upon reading it, turned to a colleague. "Here is the letter," he said, "that has destroyed my universe." By the end of 1924, Hubble had found 12 Cepheid variables in Andromeda. The result was confirmed multiple ways. The paper was announced at the American Astronomical Society's meeting on January 1, 1925. The universe was vastly larger than any pre-Hubble measurement had established. One important footnote: Hubble's 900,000 light-year estimate was an underestimate. The true distance is 2.537 million light-years, nearly 3 times farther. The error lay in the Cepheid calibration itself. There are actually 2 classes of Cepheid variable stars with different intrinsic luminosities. The Cepheids in Andromeda were the brighter class, which were intrinsically brighter by a factor of about 4. Hubble had been comparing apples to oranges without knowing it. The error wasn't discovered until 1952, when Walter Baade, using the new 200-inch Hale telescope at Palomar Mountain Observatory, resolved the discrepancy. He announced the correction at a major astronomical meeting. Someone in the audience reportedly exclaimed that Baade had doubled the size of the universe. The universe had actually been doubled twice over, first by Hubble's 1925 announcement, then corrected upward again by Baad's recalibration. But the logical conclusion of Hubble's 1924 result remained unchanged regardless of the precise distance. The Andromeda Nebula was a separate galaxy. And if Andromeda was a separate galaxy, then the other spiral nebulae almost certainly were too. Not a few of them, all of them. Every fuzzy smear and pinwheel in the sky represented a separate stellar system, each containing billions of stars, each separated from us by intergalactic distances. The universe was not 300,000 light-years across. It was not even 1,000,000 light-years across. It was a cosmos of hundreds of billions of galaxies, stretching in every direction to distances that would take Hubble himself another 5 years to begin to measure. 5 years that would produce Hubble's law, the expanding universe, and the first observational foundation for the Big Bang. Henrietta Leavitt never received a Nobel Prize. She died in 1921, 3 years before Hubble made his announcement, and the Nobel Prize was not awarded posthumously. The Swedish mathematician Gösta Mittag-Leffler is said to have been preparing to nominate her in 1924, unaware that she had died. The tool that made the measurement possible, the tool without which no Cepheid distance to Andromeda could have been calculated, was hers. But her name rarely appears in the popular accounts of how the universe turned out to be much larger than we thought. What Hubble's announcement meant, beyond the immediate conclusion about Andromeda's distance, was a restructuring of the entire conceptual framework of astronomy. If Andromeda was a separate galaxy, and if Andromeda was clearly a spiral with its arms and its disk and its central bulge, then the other spirals in the catalogue were also galaxies. Every object like Andromeda in the sky. And there were thousands in the catalogue at that point, faint smears catalogued in ever-increasing numbers as photographic plates and bigger telescopes revealed more of the sky was an independent stellar system. The universe was not the Milky Way with some gas clouds. The universe was a cosmos of billions of such systems, separated from each other by voids of intergalactic space, organized on scales that no previous observation had allowed anyone to understand. And once Hubble had the tool, the Cepheid yardstick, he could begin measuring the distances to other galaxies as well. In 1929, using distances to 24 galaxies measured by Cepheids and other methods, he published the relationship between distance and recession velocity that now bears his name. The farther a galaxy, the faster it receded. The universe was expanding. Tracing that expansion backward led to the conclusion that the universe had once been smaller, denser, hotter, to the Big Bang. All of it began with a faint, variable star blinking in a regular 31-day rhythm in a galaxy visible to the naked eye on a dark autumn night. A galaxy 900 years in the catalogue as a small cloud. A galaxy that turned out to contain the first proof that the universe was far, far larger than anyone had imagined. Now let's talk about the motion. If you point a spectrograph at almost any galaxy in the night sky and analyze the light carefully, you will find a systematic shift in the spectrum. The absorption lines, specific wavelengths at which particular elements absorbed light inside the atmospheres of stars, are displaced from their expected positions, not slightly off, not ambiguously, systematically offset toward the red end of the spectrum. The light has been stretched. The wavelengths are longer than they would be if the source were stationary. This is the Doppler effect applied to light, the same phenomenon that changes the pitch of a passing siren higher as it approaches, lower as it recedes, applies to electromagnetic waves. When a light source moves away from you, each successive wavefront is emitted from slightly farther away, stretching the wavelength toward the red end of the spectrum. The faster the recession, the greater the stretch, the larger the redshift. When a source moves toward you, the wavelengths are compressed toward the blue end. Almost every galaxy we can observe is redshifted. This is the signature of an expanding universe. In 1929, building on spectra gathered over the preceding 2 decades by Vesto Slipher and others, Edwin Hubble published his discovery that galaxies recede from us, and that the farther a galaxy is, the faster it recedes. The relationship was linear, double the distance, double the recession speed. This is Hubble's law, and it was the first observational measurement of cosmic expansion. Space itself is stretching, carrying galaxies apart, not galaxies moving through space in the conventional sense, but the space between them physically growing. Objects embedded in this growing space carry apart like raisins in rising bread. In the observable universe, there are roughly 2 trillion galaxies. Of those 2 trillion, approximately 100 show a blue shift, their light compressed rather than stretched, meaning they are moving toward us rather than away. 100 out of 2 trillion. Nearly all of those 100 belong to our local group, the small collection of galaxies gravitationally bound to the Milky Way and Andromeda, where local gravity overwhelms the background expansion of space. Andromeda is one of those 100. It is the first galaxy ever to have its approach velocity measured. The measurement was made in 1912 by Vesto Slipher at the Lowell Observatory in Flagstaff, Arizona, more than a decade before Hubble proved that Andromeda was a galaxy and not a nebula. Slipher was making a systematic study of the spectra of spiral nebulae, trying to understand their nature and composition. Measuring spectra required long photographic exposures, accumulating the faint light over many hours across multiple nights, stacking the images carefully to build up enough signal to read the absorption lines clearly. The equipment Slipher was working with was difficult. The spectrograph had to be precisely aligned. The photographic plates had to be kept perfectly still during exposures that sometimes lasted hours, tracking the movement of the sky as the Earth rotated. Every vibration of the instrument, every slight flexure of the telescope tube as it pointed at different angles, introduced error. Slipher was a skilled and methodical observer. He worked carefully and patiently over many nights. When he finally analyzed the spectrum of the Andromeda Nebula, he found it clearly blue-shifted. The object was approaching the solar system at approximately 300 kilometers per second, the highest velocity ever measured for any astronomical object at that time. This was, for many astronomers, a deeply puzzling result. If the Andromeda Nebula was a gas cloud within the Milky Way, as most astronomers still assumed, what could be driving it toward us at such an extreme speed? No known mechanism could account for it. The measurement was published, discussed, and largely set aside. Without knowing what Andromeda was or how far away it was, the velocity measurement couldn't be properly interpreted. Today, we can measure the velocity with much greater precision and with a clear understanding of what we're measuring. Slipher's 300 km figure measured Andromeda's motion relative to the Earth, which includes the Earth's orbital motion around the Sun, the Sun's orbital motion around the Milky Way at roughly 220 km in a particular direction, and the Sun's small peculiar velocity relative to nearby stars. When you subtract out all of these contributions and measure Andromeda's approach velocity relative to the center of the Milky Way itself, the figure comes out to approximately 110 kilometers per second, about 250,000 miles per hour. At 250,000 miles per hour, you could travel from London to New York in under a second. You could circle the entire Earth in about 6 minutes. You could reach the Moon in slightly under an hour and reach Mars on a favorable alignment in a few weeks. In the context of closing 2.537 million light-years of intergalactic space, this is barely a whisper. A light-year is roughly 5.88 trillion miles. The distance to Andromeda is about 15 quintillion miles. At 250,000 miles per hour, that gap would take approximately 7 billion years to close, longer than the Earth has been solid. But here's something critical about what the 110 km figure tells us, and what it doesn't. That number measures the radial velocity, the component of Andromeda's motion directed straight toward us along our line of sight. The Doppler shift measures this component precisely and unambiguously. What it cannot tell us is the transverse velocity, how fast Andromeda might be moving sideways perpendicular to our line of sight. Transverse velocity produces no Doppler shift whatsoever. Detecting it requires observing the actual angular movement of Andromeda across the sky over time, a change so tiny on human timescales that only space-based instruments operating over years can detect it. In 2012, a team of astronomers used the Hubble Space Telescope to measure Andromeda's proper motion for the first time. This meant measuring the positions of hundreds of stars in Andromeda at two epochs 7 years apart, relative to the fixed backdrop of much more distant background galaxies. The angular change they were trying to detect was roughly 6 microarc seconds per year, an angle equivalent to the apparent width of a quarter coin seen from roughly 4,000 miles away. It required stacking thousands of individual exposures and applying extremely precise calibrations to the Hubble data. The 2012 result found Andromeda's transverse velocity to be small relative to its radial velocity, consistent with a nearly head-on encounter. The analysis produced a predicted collision approximately 3.75 to 4.5 billion years from now, with a high probability of direct merger. Then, in 2025, new data changed the picture. A team led by Till Sawala published an analysis using data from both the Gaia space mission and the Hubble Space Telescope, datasets not available in 2012. The Gaia mission, launched in 2013, had spent years measuring the positions and velocities of more than 1 billion stars across the Milky Way with unprecedented precision. Combined with continued Hubble measurements, the team had a far more detailed understanding of the local gravitational environment than any previous analysis. Critically, the 2025 study incorporated two gravitational factors the 2012 model had not fully accounted for: the Large Magellanic Cloud, a satellite galaxy currently on its first approach to the Milky Way with a mass estimated at perhaps 200 billion solar masses, and the Triangulum Galaxy, the third major spiral in the local group. Both add gravitational perturbations to the Milky Way Andromeda trajectory. At the precision required to predict trajectories billions of years into the future, these perturbations matter. The revised simulations found a substantially different outcome distribution. The probability of a direct head-on collision within the traditional 4 to 5 billion year window dropped to approximately 2%. The probability of any collision at all within 10 billion years was roughly 50%. Rather than a near-certain head-on collision, the current best models show a range of possible futures. Some involve a close pass that redirects both galaxies but doesn't merge them. Some involve multiple near misses over long timescales. Some still result in merger, just later or at a different angle than the 2012 model predicted. This is not a retraction of previous work. The 2012 model was built on the best available data. Science updates when better data arrives. What the 2025 revision reveals more than anything else is that we are working with a system of extraordinary complexity projected across timescales that no instrument has ever actually measured. We can observe Andromeda now. We can measure its velocity now. We can measure its position with the best tools in the history of astronomy. And what we find is that even with all of that, the trajectory of two galaxy-scale gravitational systems across billions of years remains genuinely uncertain. Think about what that means. There is a version of the future in which the Milky Way and Andromeda pass close to each other, close enough to trigger tidal disruption in both disks, close enough to pull out long streamers of stars, close enough to trigger starburst episodes in both galaxies, but not close enough to capture each other. The two systems separate after the encounter, each carrying the scars of the passage, each transformed, but each moving on its own trajectory. No merger, a near miss at galactic scales. In that future, the local group retains two major spiral galaxies rather than gaining one elliptical. There is another version in which the encounter is more direct, and the merger proceeds more or less as the 2012 model described. A collision that begins within the next 4 to 5 billion years and proceeds through multiple passes to a full merger over the following 2 to 3 billion years. In that version, the elliptical galaxy forms. The spiral structures disappear. There are versions in between, grazing encounters that don't immediately merge, but place the two galaxies in a loosely bound orbit around each other, decaying over much longer timescales through the same dynamical friction process, eventually merging, but on a timetable of 10 or 12 or 15 billion years rather than 5. All of these outcomes are consistent with the current measurements. The uncertainty is not a failure of astronomy. It is an honest statement of what can be known from observations made on a single planet over a span of decades, projected forward across billions of years into the future of two systems of incomprehensible scale. What remains is a genuine and fascinating uncertainty. The only large galaxy in the observable universe that is unambiguously heading in our direction, and we don't yet fully know what happens when it gets here. The approach is real. The blue shift is real. The future is not fully resolved. Let's spend some time on the word collision itself, because it carries connotations at the human scale that are deeply misleading at the scale of galaxies. When two galaxies collide, the natural mental image involves solid objects striking each other catastrophically, two enormous structures slamming together. Stars exploding on impact, worlds destroyed by direct physical contact. This image is intuitive. It is also essentially wrong. To understand why, you need to understand something that numbers alone don't fully communicate: how profoundly, completely, absolutely empty a galaxy is. Consider the nearest star to our Sun, Proxima Centauri, sitting 4.24 light-years away. That distance, in miles, is approximately 25 trillion. Now, let's shrink the solar system to a model to feel it properly. If the Sun were the size of a basketball, 9.4 inches across, the size of a standard NBA ball, then on that same scale, Proxima Centauri would be another basketball sitting approximately 2,700 miles away, not across town, not in the next state. From New York, that basketball would be in the middle of the Pacific Ocean. The surface of the basketball we're standing near would represent the physical body of the nearest star to ours, the nearest one. The Milky Way contains somewhere between 200 and 400 billion of these basketballs, each separated from its nearest neighbors by distances on that same scale, thousands of miles on the basketball scale. The total volume of the galaxy is almost entirely nothing. The fraction of the galaxy's volume actually occupied by stellar material, by the physical bodies of the stars themselves, is so small that stating it as a number loses all meaning. If you were teleported to a random point inside the Milky Way, the probability of being within 10 light-years of any star at all would be low. The galaxy is, in the most rigorous physical sense, almost nothing but empty space. When two galaxies interpenetrate, which is the more accurate word than collide, their stars pass through each other like two swarms of fireflies in the same summer meadow at night. Each firefly is too small, too widely separated from every other firefly, for any direct contact to occur between two fireflies from different swarms. They occupy the same volume of air. The swarms intermix, and each individual firefly continues its own trajectory, influenced by the combined gravitational pull of both swarms, but not by any physical impact. Direct stellar collisions during a galaxy merger, the physical body of one star striking the physical body of another, are negligible events. For any individual star, including our Sun, the probability is essentially zero. Our Sun and the Earth are almost certainly safe from any direct physical impact during the Andromeda encounter. This is not a reassuring caveat. It is a precise physical prediction based on the known geometry. What does happen, and what is genuinely dramatic, just on timescales far beyond human experience, is gravity. When two massive systems pass close to each other, their gravitational fields interlock and reshape both structures. Stars in the outer regions of each galaxy feel a tidal pull from the other system, a slight but persistent difference in gravitational force across the breadth of the galaxy, stronger on the near side than the far side. This differential force stretches the galaxies in the direction of the encounter, pulling long streamers of stars outward from both systems into what astronomers call tidal tails, ribbons of displaced stars arcing outward from each galactic core for hundreds of thousands of light-years. Meanwhile, the gas in both galaxies, the interstellar medium, the raw material for future stars, gets shocked and compressed as the two systems interpenetrate. Gas clouds that have been drifting quietly through their respective galaxies suddenly encounter the density waves, pressure gradients, and heating effects of a second galaxy pushing through the same space. Under this compression, gas clouds collapse. New stars form. The star formation rate, which in both the Milky Way and Andromeda currently runs at a modest few solar masses per year, can jump by factors of 10, 50, or even 100 during intense merger events. This is a starburst, a period of dramatically elevated star formation triggered by the gravitational compression of the encounter. The best-studied example in the nearby universe is the Antennae Galaxies, a pair designated NGC 4038 and NGC 4039. They are two spiral galaxies caught in the middle of a collision that began roughly a few 100 million years ago. In photographs, they show precisely what the theory predicts. Two galactic cores still distinct from each other, surrounded by dramatically distorted and disrupted disk structures, with long, curving tidal tails arcing outward from each core, the antennae that give the pair their name. These tidal tails are hundreds of thousands of light years long. They are made of stars that were once in the outer disks of each galaxy, pulled out by tidal forces during the encounter, now drifting in intergalactic space along the trajectories their gravitational history has given them. They will remain visible as structures for hundreds of millions of years after the merger completes. The central region between the two antennae galactic cores is blazing with new star clusters. Observations in the infrared, which can penetrate the dust clouds that obscure the visual light, show hundreds of compact star clusters, many of them among the most luminous young stellar objects in the local universe. These clusters are tens of millions of years old, barely formed on galactic timescales, and they formed precisely because the gas in the two galaxies was compressed by the encounter. The star formation rate in the antennae system is estimated at roughly 10 to 50 times that of a quiet spiral galaxy. The interaction that destroys the orderly structure of two spiral galaxies simultaneously drives the formation of massive new star clusters at a rate neither galaxy could sustain in isolation. Another example is NGC 7252, sometimes called the Atoms for Peace Galaxy, a pair of galaxies photographed roughly 1 billion years after their initial collision, where the merger process is substantially more advanced. The two original galactic cores are still visible as bright concentrations within what has become a mostly elliptical structure, surrounded by rings and shells of displaced stars and extended tidal tails. 1 billion years into the process, and the transformation is still ongoing. Looking at NGC 7252 is like seeing the antennae galaxies 1 billion years into their future, a preview of what the Milky Way Andromeda system might look like long after their first encounter. The Milky Way and Andromeda encounter, if it occurs as a genuine close pass or merger, would produce versions of all of this: the tidal tales, the starburst episodes, the disruption of both spiral structures, the gradual settling of all that activity into something new. The timescales are long. Any individual moment in the process would look, to a short-lived observer, like nothing was happening. But the direction of change would be continuous. And something worth dwelling on: the stars that form in the starburst triggered by the encounter are not victims of the collision, they are its products. They are stars that would not have existed without the encounter. Massive, blue-white stars, born in the compressed gas clouds of the interpenetration, burning brilliantly for a few million years before detonating in supernovae. A new generation of stars forged in the moment of gravitational disruption. The supernovae they leave behind would seed the interstellar medium with heavy elements: carbon, oxygen, iron, silicon, enriching the gas available for the next generation of star formation. The merger, in this sense, is not purely destructive, it is transformative. It reshapes what exists. It produces what couldn't exist before. The stars forming in the antennae galaxies right now, those compact, brilliant clusters visible in the infrared, will outlast the merger process itself. Some of them, the smaller ones, will still be burning hundreds of billions of years from now, long after the two galactic disks have dissolved and reformed as a single elliptical system. They were born in the chaos of collision. They will survive into whatever calm follows. The globular clusters that already exist in both galaxies, the ancient ones, some of them 12 to 13 billion years old, will also survive the merger. They have survived everything that has happened to both galaxies across their entire histories. They survived the earlier mergers that built both the Milky Way and Andromeda into the systems they are today. There is no reason to think the Milky Way-Andromeda merger will be different. Those compact spheres of hundreds of thousands of old stars orbiting in the halo of whatever merged system forms will continue their slow circuits for as long as the merged galaxy exists. The merger destroys the organized structure. It does not destroy the stars. Let's follow the visual transformation of the sky across the timescale of the approaching encounter, because this is one of the most concrete ways to understand what the data actually implies. Right now, Andromeda is a faint smudge, visible on dark nights, easily missed, requiring dark skies and dark adapted eyes and knowledge of where to look. The galaxy that contains 1 trillion stars appears from Earth as a soft, pale oval that most people who see it for the first time think might be a cloud. The distance is decreasing. Over the next billion years, the approach is slow and continuous. The angular size of Andromeda in the sky grows. The galaxy appears brighter as the distance closes. In roughly 1 billion years, at current approach rates, Andromeda will be measurably closer, its disk spanning perhaps 3 times its current angular width. Under dark skies, it would be unmistakable to the naked eye. its elongated oval form clearly apparent without effort, its brighter central nucleus distinct from the fading outer disk. The satellite galaxies M32 and NGC 205 would be naked-eye objects in dark skies. The angular extent of the whole system might begin to approach 2 or 3 degrees. On any human scale, this change is completely undetectable. It proceeds at the rate of geological transformation, slower than continental drift, slower than the erosion of mountain ranges, slower than any process that leaves marks in the fossil record on timescales shorter than tens of millions of years. But it proceeds continuously, relentlessly. The Sun itself is changing over this timescale. The Sun is gradually brightening as it ages, its core slowly contracting and heating as hydrogen is converted to helium. Over the next billion years, the Sun will become perhaps 10% more luminous than it is today. Climate models suggest that the brightening Sun will eventually make liquid water oceans unsustainable on Earth's surface. The timeline for this is roughly 1 billion years, depending on the specific mechanisms and feedbacks involved. So, the sky that watches Andromeda grow is a sky above a planet whose habitability is already shifting on a parallel timescale. Consider what happens between 1 billion years from now and the point of closest approach. In the 500 million year range, roughly a third of a billion years out, Andromeda will be noticeably larger than today but still recognizable as a separate object. The gravitational interaction between the two galaxies will have grown stronger, and careful measurements would begin to show the first subtle signs of tidal distortion in both systems. The outer edges of both disks will have developed slight asymmetries, the outermost stars pulled fractionally toward the other galaxy's center of mass, the disk warping almost imperceptibly. No single observer would notice in a lifetime. But compared side by side, a photograph of the Milky Way from 500 million years ago and a photograph from today would show measurable differences in the shape of the outer disk. By 700 million years, the gravitational interaction would be clearly measurable in the motion of stars in the outer reaches of both galaxies. The approach of Andromeda will by then be affecting the orbits of stars far from the Milky Way's center, drawing them slightly off their circular paths. The Milky Way's warped disk, already present today, its warp attributed partly to the gravitational influence of the Magellanic Clouds, would show additional distortion from Andromeda's pull. The outer halo stars of both galaxies, already loosely bound to their host systems, would begin to be drawn slightly toward the other. In the 2 billion year range, Andromeda will have become one of the prominent visual features of the night sky. Its angular extent may span 6 to 10 degrees, covering a significant fraction of a hand held at arm's length, comparable to the angular width of the constellation Orion. The nucleus will be bright enough to rival prominent open star clusters. The outer disk, rendered more visible by the reduced distance, will be apparent to unaided eyes under dark conditions. its elongated form spanning a substantial arc of sky. The pale oval will have become something with obvious structure, a vast, organized brightness, clearly different from the background scatter of stars, clearly a distinct and enormous object hovering in the autumn sky. And the Milky Way itself will be changing. The gravitational influence of Andromeda, strengthening as the distance decreases, will begin perturbing the outer regions of the Milky Way's disk. Stars at large galactic radii will be pulled slightly from their circular orbits. The disk will develop subtle asymmetries, slightly thicker here, slightly displaced there. The clean, flat structure acquiring the first hints of distortion. The Milky Way band arcing across the sky, the pale river of starlight visible on dark summer nights, may develop slight structural irregularities, thickenings or warpings that reflect the gravitational distortion beginning to operate on the disk from outside. In the 3 billion year range, if the two galaxies are on course for a close encounter, the sky becomes genuinely different from anything that has existed in the history of the Earth. Both galaxies will be experiencing tidal interactions. Gas clouds in both systems will be compressed by the encounter, triggering starburst episodes. Hot, massive, blue-white stars, the kind that burn through their fuel in only a few million years before dying in supernova explosions, will be forming in large numbers in both galaxies. From Earth's surface, this means a sky richer in bright young stars than anything in the current sky. The Milky Way band will be brighter and more structurally complex. There will be regions of active star formation visible as diffuse glows, pink-red emission nebulae where hydrogen gas is ionized by young star clusters, blue-white reflection nebulae where dust scatters the light of massive new stars, scattered through the sky. Supernovae will be more frequent than they are today. In the current era, a supernova occurs somewhere in the Milky Way roughly once every 50 to 100 years. During an active starburst triggered by the merger encounter, the rate could increase substantially as more massive, short-lived stars form and detonate on compressed timescales. Some of these supernovae would be briefly visible in daylight, spectacular events in the sky, new points of light appearing and fading over days or weeks. Andromeda by this point may span 20 to 30 degrees of sky, large enough that looking from one side of it to the other requires turning your head. Two bright concentrations will be visible simultaneously, our own galactic center glowing in the direction of Sagittarius and Andromeda's core, a competing brightness in the autumn sky. Between them, in the space where the two galaxies are beginning to overlap, faint arcs of displaced stars, tidal tails in formation, will be visible in long photographic exposures. The tidal tails, as they develop, will extend across the sky as faint rivers of starlight, streams of displaced stars caught in the process of being redistributed by the gravitational interaction. In long exposures, these structures would be magnificent, comparable in scale to the Milky Way band, but fainter and more diffuse, arcing through the sky like pale brushstrokes. It is not a frightening sky, it is a complicated one, rich, active, full of structure that the current sky lacks. The constellations as we know them will be unrecognizable long before this point. Proper motions of nearby stars over billions of years will have shuffled the patterns into configurations no current observer would identify. But the overall brightness and structure of the sky will be more dramatic, more organized, more visibly indicative of the forces at work. It is also worth noting what would not change during this transformation. The solar system itself, the sun, the planets, the comets and asteroids orbiting quietly at distances of billions of miles, would continue its slow orbit around whatever gravitational center exists at any given stage of the merger. The stars of the Milky Way do not know about the merger on any local scale. They continue to burn hydrogen in their cores. They continue to move through the interstellar medium on their own trajectories. The Earth, if it still exists as a habitable world, would orbit the Sun on exactly the same timeline as it does now. The merger happens around the solar system. It does not happen to it. What would change, from any perspective on Earth, is what you see when you look up. The sky, the ever-present display of other suns and their organized patterns, the Milky Way band, the familiar geometry of a disk galaxy viewed from within, would be transforming on timescales measured in hundreds of millions of years. Any given observer would notice nothing in a lifetime. But the sky of the first encounter is different from the sky of the second. The sky of the second is different from the sky after the merger completes. The transformation is real even if no individual observer can watch it happen. Whatever exists on Earth or near the Sun at that time will not be human. The Sun will be approaching or entering the later stages of its main sequence life, gradually brightening over billions of years and making Earth's surface hotter and eventually uninhabitable to water-based life long before the galactic merger is complete. But stars do not know this. They continue burning. And if something capable of watching the sky exists at that time, what it sees will be one of the most dramatic astronomical environments in the history of our corner of the universe. Let's follow the story to its conclusion, or as far as current models can project it. If the Milky Way and Andromeda do meet in a close encounter, the process plays out in multiple stages across billions of years. The first close pass occurs. The two galactic disks interpenetrate, the stars of each passing through the vast empty spaces of the other, undisturbed by direct contact but profoundly disturbed by gravity. Both galaxies are deformed. Tidal tails stream outward from each system. Gas clouds collide and compress, triggering bursts of star formation. The spiral arms of both galaxies begin to be disrupted, pulled into asymmetric, distorted configurations rather than the clean logarithmic spirals both currently show. Then the two systems move apart. The momentum of the approach carries them through and past each other, and for a period that may last hundreds of millions of years, the two galactic cores are again separated. The sky would show two distinct, disturbed systems, clearly interacting, trailing long tidal streamers and bright with new star formation, but occupying separate regions of sky. Something resembling the antennae galaxies as we see them today, two distinct, deeply disrupted spirals with the evidence of their interaction everywhere in their structure. But gravity draws them back. The kinetic energy of the encounter has been redistributed, transferred into heating the stellar populations, into driving the tidal material outward, into the disordered motion of stars disrupted from their original orbits. The two systems no longer have enough total kinetic energy to fully escape each other. A second close pass occurs. More disruption, more star formation, more tidal material scattered, and again they separate slightly, and again gravity pulls them back. This process, the gradual decay of the orbital energy through repeated interactions, technically called dynamical friction, repeats. Each gravitational encounter transfers energy from the orbital motion of the two galactic cores into the random motions of the stars around them. With each cycle, the two cores come closer together. Eventually, the two cores can no longer meaningfully separate. They merge. Computer simulations of this process, run by T.J. Cox and Abraham Loeb at Harvard-Smithsonian, and by other groups using increasingly sophisticated numerical codes, find that the merger takes place over a period of roughly 2 to 4 billion years from the first close encounter. The simulations typically show 2 or 3 close passes before the final merger, with each pass becoming closer and shorter than the previous one. The simulations also find results for specific objects like the solar system. In different simulation runs, the Sun-like objects end up in widely varying positions in the final merged galaxy, some in quiet outer regions, some in the central bulge, some in tidal streams far from the main body. The specific outcome is sensitive to small differences in initial conditions in ways that make deterministic prediction impossible. We cannot currently predict where the solar system will end up. What we can say is that the Sun itself will almost certainly still exist as a star. Stars are not endangered by galactic mergers in the physical sense of being destroyed by them. Some simulation runs show the solar system being flung outward, ejected into the extended halo of the merged galaxy, or into one of the tidal tails, where it would find itself in an environment of much lower stellar density than the current neighborhood. A star in a tidal tail is effectively in intergalactic space with a few scattered companions, far from the bright concentration of stars in the main body of either galaxy. In that scenario, the night sky from a planet in the solar system would be dramatically different from today's sky. Not the dense band of the Milky Way arching overhead, but a sparse scatter of distant stars and the glow of the merged galactic core seen from outside, like a view of a galaxy from intergalactic space. In other simulation runs, the solar system ends up in the central bulge of the merged galaxy, a far denser environment. In the bulge of an elliptical galaxy, stars are separated by somewhat smaller average distances than in the outer disk. Though still vastly separated by everyday standards, the night sky would be brighter, more stars visible per square degree, no preferred plane of the Milky Way band, just a roughly uniform distribution of stars in every direction. In the very center of the merged galaxy, near the merged supermassive black hole, the stellar density rises to levels that would produce a noticeably brighter night sky than anything we experience today. In either scenario, the solar system persists. The orbits of the planets continue. Whether the Earth would still be habitable, given the Sun's ongoing brightening over the billions of years it takes to reach these merger scenarios, is a separate question, one that depends on factors entirely independent of Andromeda. The answer, from what we understand of stellar evolution, is almost certainly no. But the solar system as a physical structure, a star, and its companions moving through the universe, continues. What changes is the context, the neighborhood, the sky, the galactic environment that the solar system inhabits and that shapes in subtle ways everything from cosmic ray flux to the probability of long-period comet impacts. The merger doesn't end the solar system, it just moves it somewhere it has never been. The merged system, in the models, is a giant elliptical galaxy, not a spiral, not a disk, a roughly spherical or lens-shaped collection of stars slowly rotating in no preferred direction, lacking the organized flat structure of either parent system. The spiral arms of the Milky Way will be dissolved. Andromeda's spiral structure will be equally gone. The flat disk we live in, the structure that gives us the pale band of the Milky Way across the sky on a clear night, will no longer exist as a coherent feature. Why an elliptical? The flat disk of a spiral galaxy requires that the stars orbit in organized coplanar paths in the same direction. This organization is maintained by the original angular momentum of the gas cloud from which the galaxy formed. When two disk galaxies merge, their disks have different orientations and angular momenta. The gravitational interaction of the merger shuffles the stars into new orbits, randomizing the directions and inclinations. Stars that were once orbiting in an organized plane are flung into complex, three-dimensional orbits in every direction. A system of stars in disordered three-dimensional orbits is, by appearance and by dynamics, an elliptical galaxy. Red, smooth, featureless in structure, quiet in star formation. The combined globular cluster system of the merged galaxy will be extraordinary. The Milky Way contributes approximately 150 to 200 globular clusters. Andromeda contributes more than 450. The merged system will have a globular cluster population larger than either parent, carrying forward these ancient, dense, stellar systems, some of them formed in the first billion years of the universe's history, into the new elliptical galaxy. These objects are the survivors, They have already outlasted many earlier galactic structures. They will likely outlast the merger itself as distinct objects. The elliptical galaxy that results from the merger will look nothing like either of its parents from the outside. Elliptical galaxies are the most common type of galaxy in the dense centers of galaxy clusters. They are smooth, featureless, roughly ellipsoidal or spherical collections of stars glowing with the warm orange-red light of old stellar populations. No spiral arms, no disk, no obvious structural features visible to a distant observer beyond the gradual brightening toward the center. No dense, cold gas. No active star formation to speak of. In photographs that show spiral galaxies in vivid detail, the blue arms, the pink star-forming regions, the dark dust lanes threading through the disk, elliptical galaxies appear as smooth orange ovals, quiet, simple in appearance, though not in dynamics. This simplicity is the result of age and history. An elliptical galaxy is not a galaxy that never had structure. It is a galaxy that had structure and lost it. The structure was destroyed by merger events, the same kind of event that will produce the Milky Way Andromeda merger product. The stars that were once orbiting in organized disks now orbit in disordered, overlapping three-dimensional paths. The organized blue star-forming regions are gone because the cold gas that fed them has been consumed or heated. What remains is the slow, quiet, stellar inventory of a system that has been through something. From within an elliptical galaxy, from whatever position the solar system occupies in the merged system, the night sky would look different. There would be no Milky Way band, no flat disk to be seen as a river of light across the sky. Stars would be distributed more uniformly in all directions. In the outer regions of the merged galaxy, the star density might actually be lower than the outer Milky Way today. In the inner regions, near the center, the star density would be dramatically higher, potentially thousands of times the density of stars near the Sun. Both environments are possible destinations for the solar system during the merger, and simulations suggest both are realized in different runs with slightly different initial conditions. The merged galaxy will be quieter than either of its parents, but it will not be empty, and it will not be dead, just old and reorganized, and carrying the history of everything that made it. Now, there are the black holes. Andromeda's central supermassive black hole, 140 million solar masses, and Sagittarius A star, 4 million solar masses, will both sink toward the center of the merged system through dynamical friction, losing energy to gravitational interactions with the surrounding stellar population. Eventually, they form a binary, two enormously massive objects in close orbit around each other. The mechanism by which this binary continues to spiral toward merger involves what's called the final parsec problem, the difficulty of getting two black holes closer than roughly 1 parsec, about 3.26 light-years of each other. At larger separations, the binary loses energy efficiently by flinging nearby stars to high velocities. Those stars carry energy away from the binary and bring the two black holes closer. But eventually, the supply of stars in orbits that efficiently interact with the binary gets depleted. Stars that were accessible have already been ejected. Some additional mechanism, gas dynamics, triaxial galaxy shapes sending new stars into the binary's influence region, must bridge the remaining distance. When the two black holes finally merge, the event will radiate an enormous burst of gravitational waves at frequencies in the millihartz range. The amplitude and frequency place this event firmly in the target band for LISA, the Laser Interferometer Space Antenna, a gravitational wave observatory planned by the European Space Agency. A future LISA successor, operating when this merger eventually occurs, would detect it as one of the loudest gravitational wave sources in the observable universe. The final inspiral of 200+ million solar masses of compressed spacetime, spiraling together at a significant fraction of the speed of light, will send ripples through spacetime detectable across the local group and far beyond. Now let's zoom out one final time to the largest context our situation sits within. Andromeda and the Milky Way exist within the local group, a gravitationally bound collection of approximately 54 known galaxies, spread across a region of space roughly 10 million light-years across. Most of these are dwarf galaxies, small, irregular, faint collections of stars orbiting one of the two dominant members. But collectively, the local group is a distinct structure, held together by its own gravity against the universal expansion pressing outward everywhere around it. The three largest members are the Milky Way, Andromeda, and the Triangulum Galaxy, M33, a spiral galaxy approximately 2.7 million light-years away, containing roughly 40 billion stars. Triangulum is diffuse and loosely structured, its spiral arms less organized than either Andromeda's or the Milky Way's. Under genuinely exceptional sky conditions, very dark, very transparent, very well dark-adapted eyes, Triangulum is just barely detectable as a faint smudge to the naked eye, making it one of only two external galaxies the unaided eye can reach, alongside Andromeda. Most observers who claim to see it are not sure they're seeing it. It is right at the edge of what the human eye can detect. Beyond the three major spirals, the local group contains the large and small Magellanic Clouds, irregular satellite galaxies of the Milky Way, visible from the southern hemisphere as bright patches distinct from the main arc of the Milky Way. The large Magellanic Cloud in particular is a substantial system containing tens of billions of stars, several hundred light-years in extent, massive enough to have left measurable gravitational imprints on the structure of the Milky Way's own disk. Recent measurements using the Gaia satellite suggest the Magellanic Clouds may be on a first infall, approaching the Milky Way for the first time, rather than completing a repeated orbit. If so, they will be gradually absorbed over the next several billion years. All of these galaxies are gravitationally bound to each other. The gravity of the local group exceeds, in this local region of space, the outward push of dark energy. The members of the local group will not be pulled apart by the cosmic expansion. They are bound together. The local group itself is part of larger structures. It sits within the Virgo supercluster, a gravitationally influenced region centered on the Virgo cluster, roughly 53 million light-years away. The Virgo supercluster is itself now understood to be part of an even larger structure, the Laniakea supercluster, mapped and named in 2014 by Brent Tully and colleagues. Laniakea, the name comes from Hawaiian, meaning immeasurable heaven, is a vast complex of superclusters, filaments and voids roughly 520 million light-years across, containing about 100,000 galaxies and a total mass estimated at 100 million billion solar masses. The Milky Way sits on the outer edge of Laniakea, near the boundary between Laniakea and an adjacent supercluster structure. This is the large-scale context. Individual stars in galaxies, galaxies in the local group in the Virgo supercluster, the Virgo supercluster in Laniakea. Laniakea in the cosmic web of superclusters and filaments that defines the largest observable structures in the universe. Dark energy is what's governing the fate of all of this at the largest scales. It was identified definitively in 1998 when two independent teams studying distant Type Ia supernovae, stellar explosions of calibrated luminosity used as standard candles, found that distant supernovae were dimmer than expected for a uniformly expanding universe. The universe was not just expanding, the expansion was speeding up. Something was pushing it apart faster and faster over time. That something was designated dark energy because it clearly has energetic effects on the universe at the largest scales, and we have no idea what it actually is. It is not any known particle. It is not any known field. It does not interact with ordinary matter except gravitationally. It constitutes approximately 68% of the total energy density of the universe according to the best current measurements. The remaining 32% is split between dark matter at about 27% and ordinary matter, everything visible, everything made of atoms, at about 5%. We understand dark matter imperfectly and dark energy hardly at all, yet together they account for 95% of the energy budget of the universe. The simplest interpretation of dark energy is that it represents a fundamental property of space itself. That empty space has an intrinsic energy density, sometimes called the cosmological constant, that doesn't dilute as the universe expands, unlike matter or radiation. Other interpretations involve a dynamical field that can vary over time and space. As of now, the observational evidence cannot distinguish between these possibilities. We know what dark energy does. We do not know what it is. What dark energy does is drive the metric of space to expand. For sufficiently distant galaxies, the recession velocity exceeds the speed of light. Not because anything is moving faster than light through space, but because the space between us is growing so rapidly that light traveling across it can never arrive. The light from those galaxies sent long ago will never reach us. They are, in a physically meaningful sense, already gone from our observable universe. Right now, the observable universe contains roughly 2 trillion galaxies, but that number is shrinking. As expansion continues to accelerate, more galaxies cross the horizon, more light is permanently stretched beyond detection. On timescales of tens of billions of years, the universe as we can observe it will be transformed. In roughly 100 billion years, galaxies outside the local group will be far beyond any cosmological horizon. The great filaments and walls of the cosmic web will all be beyond any possible detection. No light from any of those structures will be reaching the local group. If something existed in the local group at that time and tried to study the universe, all of cosmology, the evidence for cosmic expansion, the existence of billions of galaxies beyond our neighborhood, the Big Bang itself as implied by the recession of distant galaxies would be invisible. The observable universe would be only the local group. By then, the local group itself will have consolidated. The dozens of dwarf galaxies orbiting within it will have been absorbed by the larger systems over the preceding tens of billions of years. What remains will be a small number of large, old, mostly elliptical galaxies, products of mergers, including the Milky Way Andromeda product, slowly consuming their last reserves of available star-forming gas. The Triangulum Galaxy, M33, the third largest in the local group, may have merged with Andromeda even before the Milky Way does, given the uncertainties in its own trajectory. The Magellanic Clouds will almost certainly have been absorbed by the Milky Way long before any Andromeda encounter occurs. The dozens of dwarf spheroidal galaxies orbiting within the local group, small, faint systems containing millions rather than billions of stars, many of them barely detectable even with modern instruments, will slowly be consumed or tidally disrupted by the major galaxies as their orbits decay over billions of years. Each one contributes its stars to the inventory of the larger system that absorbs it. The process of galaxy eating, of large systems growing by consuming smaller ones, has been ongoing since the earliest galaxies formed, more than 13 billion years ago. Both the Milky Way and Andromeda are not primordial objects unchanged since their formation. They are composites, assembled over billions of years from many smaller systems, each merger leaving its traces in the stellar populations, the chemical gradients, the stellar streams and shells that surround both galaxies. What we call the Milky Way today is the accumulated product of billions of years of mergers and accretions. The merger with Andromeda is the next chapter in a process that has been ongoing for the entire history of the universe. New stars will have become rare. The universe's supply of cold gas has been consumed and processed over billions of years. What remains will be largely locked in stellar remnants, white dwarfs, neutron stars, black holes, rather than available to form new stars. The remaining stars will be dominated by red dwarfs, small, cool, faint stars that burn their nuclear fuel extremely slowly. A star with half the Sun's mass can live for roughly 50 billion years. A star with 1/10 the Sun's mass may live for 10 trillion years or more. These small, dim stars will outlast every other kind of stellar object by enormous margins. In the far future of the universe, the sky, as viewed from inside the local group, will contain no hot blue stars, no bright yellow dwarfs like the Sun, no supernovae, just dim red lights burning slowly. Eventually, even those run out. The red dwarfs exhaust their hydrogen and fade. The white dwarfs, cooling remnants of sun-like stars, continue to cool, dimming from white to yellow to orange to red, and finally to dark. On timescales of many trillions of years, the white dwarfs become black dwarfs, cold, dark, inert objects that emit essentially no light and no heat. The universe cools. The available energy density drops. It is a slow process, not a catastrophe, not an explosion, just the gradual running down of all the physical processes that have been operating since the Big Bang. Entropy increases, free energy becomes scarce. The time scales involved in all of this are worth trying to hold in the mind, even though they resist it. The current age of the universe is approximately 13.8 billion years. The Sun will exhaust its main sequence hydrogen fuel in roughly 5 billion more years. The last red dwarf stars will burn for perhaps 10 trillion years, about 700 times the current age of the universe. After that, the only stellar remnants will be white dwarfs cooling toward absolute zero, and the era of stellar light in the universe will be over. After the stars, astronomers project what is sometimes called the degenerate era, a period lasting perhaps 10 to the power of 40 years, during which the universe is populated by slowly cooling white dwarfs and neutron stars orbiting each other in arrangements that grow increasingly sparse as gravitational interactions eject them from their mutual orbits over vast timescales. The numbers at this stage are so large they become difficult to write down meaningfully. 100 million trillion years, and the universe will still exist, quiet, cold, dark, but not yet done. After the degenerate era, the black hole era. The remaining black holes, including the supermassive ones at the centers of galaxies, will slowly evaporate through Hawking radiation, a quantum mechanical process predicted by Stephen Hawking in 1974. The evaporation of a supermassive black hole containing hundreds of millions of solar masses would take on the order of 10 to the power of 100 years, a duration that makes the current age of the universe look like a fraction of a nanosecond by comparison. But it would happen. Even the most massive objects in the universe are not permanent. Eventually, the last black hole evaporates. The universe contains nothing but the most diffuse imaginable collection of photons and fundamental particles spread across a space that has expanded to unimaginable scale. This is heat death, not a dramatic ending, not an explosion, but the completion of a process of cooling and dispersal that began with the Big Bang. Maximum entropy, no more free energy gradients to drive any physical process. This is the universe's future, not catastrophe, not collapse, just gradual quieting. The slow recession of everything beyond reach, the long drawing in of the curtain. A universe that started in extraordinary density and heat, expanded through a long, productive middle age of star formation and galactic evolution, and then grew old and quiet and empty in a way that mirrors the eventual cooling of a fire that has burned through all its fuel. And it is already beginning. The galaxies beyond the local group are accelerating away. Some have already crossed the horizon. The universe is becoming very gradually a smaller and quieter and more isolated place. The one thing that isn't receding is Andromeda. Now, as we approach the end of tonight's journey, let me bring it back to where we started. That pale smudge. You can see it with your naked eye on a clear night from a dark enough place. A faint oval glow in the autumn sky, easy to miss, easy to confuse with something unremarkable. The collective light of 1 trillion stars, thinned by 2.537 million light-years of intergalactic space, into something you could cover with your fingertip. Here is what you are actually looking at. You are looking at the only large galaxy in the observable universe that is approaching us rather than receding. You are looking at a system that carries, at its heart, a supermassive black hole 35 times more massive than the one at the center of our own galaxy, surrounded by a double stellar nucleus unlike anything in our immediate cosmic neighborhood. You are looking at the object that, when one man found a single, faint, variable star within it in October 1923 and measured its distance, instantly made the universe 1,000 times larger than anyone had believed. You are looking at a system measured and catalogued and argued over for more than 1,000 years of recorded astronomy, and that still, in 2025, surprised us with the news that its future, our future, is less certain than we had concluded. It was there when Abd al-Rahman al-Sufi noted it as a small cloud and recorded it and moved on. It was there when Immanuel Kant proposed, without any way to test the idea, that the universe might contain island universes comparable to the Milky Way. It was there when Shapley and Curtis stood in a room in Washington and argued about the size of everything, each man right about some things and wrong about others, neither one able to resolve the question that evening. It was there when Henrietta Leavitt found the relationship between period and luminosity in Cepheid variable stars, building the tool that would eventually measure its distance, without ever knowing it would be used this way, without ever receiving full credit for the discovery during her lifetime. It was there when Hubble examined his photographic plates in 1923 and found a variable star blinking in a 31-day cycle, and understood what it meant, and understood that the universe was larger than anyone had imagined. It was there when Walter Baade corrected the calibration in 1952 and the universe expanded again, further still, to the distances we use today. It was there when Till Sawala and his colleagues ran their simulations in 2025 and found that our predicted collision was less certain than we thought, that the fate of 2 trillion stars is still not fully written. And it is there tonight, and it will be there when everything we know about the night sky has changed, when the spiral arms are dissolved, when the disk of the Milky Way no longer exists as a coherent structure, when the merged elliptical galaxy quietly burns through its last generations of red dwarfs in a universe from which everything else has receded beyond reach. The thing about Andromeda is that it doesn't know we're here. It carries no awareness of the Milky Way, no intention of arrival, no sense of what its light means when it crosses 2.537 million light-years and reaches a pair of eyes on a small rocky planet in the outer reaches of a neighboring galaxy. It is simply following the oldest and most fundamental rule in the universe. 2 objects with enough mass and nothing powerful enough to stop them will, given enough time, find each other. Gravity doesn't negotiate. It doesn't rush. It doesn't pause. It accumulates continuously at every scale for as long as matter exists. It has been accumulating between Andromeda and the Milky Way for the entire lifetimes of both galaxies, for 10 billion years, for longer than the sun has been burning, for longer than the Earth has been a solid world, and it continues right now, tonight at 110 kilometers per second, closing a gap that is still measured in quintillions of miles. What happens when the gap closes remains, as of tonight, genuinely uncertain. The universe does not owe us a predictable future at this scale. The new measurements say so clearly. A 2% chance of head-on collision within 5 billion years, 50% odds of any collision within 10 billion years. A range of futures, each one a different story for the same set of facts. But on a clear, dark night, you can look up and see it. That pale smudge in the autumn sky, that ancient light. 1 trillion stars compressed by distance into something smaller than your thumbnail, not drifting away, not receding with the rest of the universe, arriving. It has been traveling toward us for longer than the Earth has existed, and tonight it still has a long way to go. Thank you for spending tonight here with me, exploring one of the most extraordinary objects in our sky. If this journey moved something in you or made the night feel a little wider and a little more real, consider liking this video and subscribing to Slow Orbits. It means a great deal. Sleep well.